So our next speaker is Celia Mulcahey. I hope I pronounced it correctly. Very close. So examining a rapidly rotating redshift 2 galaxy using JWST, NIRSpec, Slitlet, stepping.
Okay, is this good, the microphone? Okay. All right. Well, at first, I'll introduce myself. I'm Celia Mulcahey. I'm a rising third year at Johns Hopkins University. I work with Susan, and I'd like to take the opportunity to thank collaborators and also the organizers of the conference, especially for scheduling me right after Susan, after doing the heavy lifting of describing our survey. And I'm excited to talk about one of the 56 galaxies that we observed. We call it the Bear Claw Galaxy, which is a massive, highly star-forming galaxy at redshift 2. And depending on how hungry you are right now or how creative, you might know where its namesake comes from, which is a bear claw pastry. So on this slide, I show from left to right a UV color diagram, star formation main sequence, and then size versus stellar mass. And if there's something that I want you to take away from this slide is that compared to redshift 2 galaxies, the bear claw is slightly dustier, slightly more massive in star forming, and larger. And based on these plots, you might not think that this galaxy is exceptionally different from redshift 2 galaxies. And here I show a broadband image from JADES and two single bands in the rest near UV and near IR. And something that I want to just point out is that the visual morphology of this galaxy is complex. It's asymmetric, and in the near UV, it's very clumpy and highly attenuated in the center. But then when you move to the near IR, where the light is coming from stars that predate the most recent bursts of star formation, you're looking at stars that make up the backbone of the galaxy. You have something that may be like a spiral arm. It kind of looks like that, and then there's this bar-like feature in the center. And on this slide, I show our slitlet stepping, but you might want to call it slitlet dancing with the dithering. Here's a GIF of our slitlet stepping pattern for this galaxy, and I show the corresponding 2D spectra on the top. And you can see that we really sampled this galaxy nicely. It was chosen because it is very extended, and we wanted to really see what this IFU-like map would be from our data. And before showing our data cube, results from the data cube, I just want to start with the 2D spectra itself. And here I've kind of rotated the picture from the previous slide to show that the slit kind of running down the center of the galaxy next to a spectral cutout around H alpha and N2. And this, the y-axis is spatial extent, and we have wavelengths on the x-axis, and I've lined it up to match where I kind of expect this to correspond to in the image. We have like more 2D spectra up here, which is the sky. I've just put that just for ease of viewing. And as you can see, the lines H alpha and N2 are tilted, which indicates rotation. And here I kind of snip it more to H alpha and just going in each row, fitting just a simple Gaussian to H alpha. We see that the max blue shifted velocity is around 247 kilometers per second, and the maximum redshifted velocity is 235 kilometers per second. And on the next slide, I'm going to show you the H alpha velocity map, which we created from combining these 30 2D spectra into data cube, which Susan briefly mentioned that what we did. And so I show a familiar picture of the bear claw from the JWST imaging. It's about 3 arcseconds across, and this white bar indicates 1 arcsecond, which at this redshift is about 8.5 kiloparsec, or 8.2. And here I show the H-alpha velocity map. Every pixel that you see on this map has a signal-to-noise greater or equal to 3. It's kind of like a draconian cut just to show our best fits, of course, with, you know, keep reducing the data in better ways, and we're going to extend the map further, but for now I'm just showing our best fits. And again, you see that it's kind of rapidly rotating at like plus or minus 320 kilometers per second. On the next slide, I'll show the actual numbers. And I just want to point out that these velocities are not corrected for an inclination. I'll talk about that in a couple slides. And previously I showed the rotation curve from H-alpha from the 2D spectra. And on the velocity map, I overlay in cyan where the 2D spectra came from roughly. And then the dashed line, I show where we believe the kinematic major axis of the galaxy is. And along this line, I extract the velocity of H-alpha pixels that are along the kinematic axis, and I plot them here. So you see that it has a maximum redshift velocity of 259 kilometers per second and a maximum blue shift velocity of negative 315 kilometers per second. So again, it's rotating quite rapidly, and also it doesn't have symmetric rotation. Something that I also want to mention that I wanted to say last slide is that the zero velocity line isn't like a straight line. It has this S shape, which we're still looking into, like what is exactly causing that. We think this bar-like feature might play into that, but we can't say anything with certainty. We're still exploring all of our options. And on the next slide, I am going to show pretty much the same thing, but I'm going to show the rotation curve folded. So I'm going to put the red side of the rotation curve and the blue side of the rotation curve overlapped on one another, so we can compare how the two sides look. And this is it. So up until about 4 kiloparsecs, the rotation curves, they look pretty similar, which is nice, but they then diverge around like 4 or 5 kiloparsecs. And you know, when we extend this map with future reductions, we're interested to see, you know, will the blue shifted side flatten out, or you know, will this rise again? But yeah, this is the format of the rotation curve that I will be showing from now on, a folded rotation curve. And the arrow bars on this plot are 10 kilometers per second. Again, we had a resolution of 3,000, and we expect that the errors are between 5 and 10 kilometers per second. I'm working on measuring formal errors, but this is just a for now error. And our greatest uncertainty actually in the velocities is due to inclination. And here I show 2 stretches of the F44W band, and I did isophoto fitting, and I decided to measure the inclination at R of 25, which is the isophoto radius where the surface brightness is 25 magnitudes per arcsecond squared. And at this radius, I get a inclination of 30. And again, more rigorous modeling would be needed to get formal errors on this inclination. I've, for now, kind of thought it could be around plus or minus 15 degrees. It could be more. But for now, like moving forward, I'm just going to use 15 degrees as the error. But just keep that in the back of your head. And so now I'm going to show you the rotation curve corrected for inclination. So at the velocity at a given radius, you divide it by sine of the inclination. And you see that with the inclination effect taken into account, it goes up to around 500, 600 kilometers per second on either side. And the error bars kind of represent, you know, what if it was actually inclined at 15 degrees? This blue shifted side actually goes up to something closer to 1,200 kilometers per second, and the red shifted side to 1,000, which is kind of absurd, but we're going to stick with 30 degrees for now. And, you know, when we saw this, we were just really shocked. Like, it was amazing to see this rotation velocity map, and instantly we're like, okay, what is, you know, this is the observed rotation curve, but what are the components of this rotation curve doing? So over the past few months, I've been working on decomposing this observed rotation curve into the inferred rotation curve of the stars and then of the gas. And so to do this, you know, we've done some SED fitting to available candles, bands from HST, as well as JADES. Ezra has been leading the SED efforts in the group. And from the stellar mass map, I've done a radial profile and used gypsy rope mod to create a like a inferred stellar rotation curve, which you see plotted here. And then the errors again on this, the shading is due to the uncertainties in the inclination, and we see that the stars have a maximum velocity of around 258 kilometers per second. And then this is where it gets very preliminary. I'm still working on this, but I was really interested to see the contribution from gas to the observed rotation curve. And so, you know, I had to do some conversions from our star formation rate map into a mass of the gas map. And to do that, you know, we used Kennekin-Schmidt relation as well as, you know, like observed, you know, relations between the infrared luminosity and molecular gas luminosity. And what I'm working with now is just a first order kind of estimate. We have like archival ALMA and Spitzer data, so we have the far IR bands, that we're going to incorporate into our SED fitting to get a better kind of star formation rate measurement to, you know, improve what I'm going to show you now, which is the rotation curve from the gas. And again, this is just, you know, the gas map with the radial kind of profile, putting it into gypsy rope mod, and we see that it could have a velocity of around 397 kilometers per second. This is very preliminary, and, you know, I'm going to be working on, you know, improving this measurement and trying to understand what is the gaseous component doing. And then I'm just going to kind of leave it off that here, if we add in quadrature the rotation curves from the stars and the gas, you know, it doesn't fully account for the rotation that we see in the outskirts of the galaxy from H alpha. And I briefly mentioned that in the future we're going to put the far IR bands into our like SED fits to get a better measurement of star formation rate, which will you know, give us a better kind of understanding of, you know, the gas rotation curve. And then you know, I'm going to model the dark matter rotation curve, see if it follows an NSW profile or something different. And, you know, it's just going to be really fun and interesting, and it's just a delightful galaxy to work on. So I'm just going to leave it there, and yeah, thank you.
Questions?
A very interesting result. The red part of the rotation curve actually drops towards the outer radii. Do you think it's real?
Yeah, so, yeah, that's a good question. I think I'd like to see the math, our H-alpha math, go out a little bit further with future reductions. Yeah, it's hard to say if it's real or not. I don't know if it's flattening out there, or if there's something with the potential FAR that might be making it go down and come back up. But that's something that I have been thinking about. But I can't really say anything for certain.
Nevertheless, very interesting. Thank you.
Marcus.
So that's a very impressively large velocity, and I'm just wondering, objects with circular velocities that high must be incredibly rare.
Mm-hmm.
Given your survey volume,
Mm-hmm.
I mean, is it really a priori unlikely that you would find such a thing? I mean, should you be worried about finding something with that large a velocity given your survey volume?
Yeah, that's a good question. I mean, I don't think we were expecting to get this result from this galaxy. When we think about like local disks, they rotate around 120, 200 kilometers per second, and it's the largest objects at like 80 kiloparsecs that have these like very large rotations. This is a small galaxy. It's rotating pretty rapidly, so I don't know what our like an a priori of predicting.
Well, I guess what I mean, for example, you must have, right, in order to rotate this fast, there must be some sort of, you could say, what's the minimum halo mass that I need?
Yeah.
Right? You think you know sort of what the halo mass function looks like as a function of redshift. You know how much volume you surveyed at what redshift, and so you can ask, right, is the expected number of objects with this mass in my field a big number compared to 1 or a small number compared to 1?
Probably a small number. Yeah.
Right, but can I add a comment on this? If you see the Bmax versus halo mass relation, a fixed halo mass, Bmax increases at higher redshifts. So I mean, yes, because the universe was denser in the past, so that's why you have higher Bmax velocities at higher redshifts. So even though I believe it's a very high velocity, but probably it's not that crazy.
Okay. This is a quantitative question that can't be answered.
Right. Yeah. Of course. A very interesting question.
Thank you, Celia, for the nice talk. And I don't know if I missed at the beginning. Do you have any guess about the environment of this galaxy?
Yeah, that's.
Because I don't know
did
if
mention that.
maybe it's something that is the result of an ongoing merger, or I mean, maybe there's a bar over there, but
Yes.
the zero velocity curve, the zero velocity in the map,
Yes.
right, has these weird shapes. So maybe something ongoing there, and of course the dark matter rotational curves.
Yes. So I forgot to mention this. So this is an image in the rest near UV and the rest near IR, and there was this like little. It's not an interloper because it's at a higher redshift, like right here. It's not at the same redshift, but we kind of. It's pretty alone, if that makes sense. There's really nothing around it at the same redshift, and when we kind of look at these images in different stretching, there's nothing that jumps out, at least to me, that says there's like major interaction happening present.
Okay. Let's thank Celia again. Our next speaker